Okay, now that we have that regular partition defined, let's look at the definition of a Riemann sum. Okay. So a Riemann sum is defined this way. We've got f as a function defined in a closed interval, which is divided into n subintervals of equal length, delta x. If xk star is any point in the kth interval, then this sum of f of x1 star times delta x plus etc. f of x2 star times delta x is called the Riemann sum. Okay, and again, the Riemann sum is for calculating area. So we can also say area is equal to the sum of all those because each one's the length times the width for the rectangle. Now, to be a little more specific, like how do you find xk star? There are 3 different ways to find that xk star. We already know how to find delta x, right? Delta x was defined above. We know how to find that one. What we need to know is how do I define xk star? So there are 3 types that are commonly used. There are other types as well, but these are the 3 most common. We have our left Riemann sum, our right Riemann sum, and our midpoint. Riemann's just a guy's name that decided he liked sums a lot. So we have the left Riemann sum, where you choose xk star to be the left endpoint. Okay, there's a picture on the next page. We'll talk about that. We have the right, where xk star is defined to be the right endpoint, and the midpoint, where xk star is chosen to be the midpoint. Okay. Now, these aren't usually used separately. They're usually used in conjunction with each other. Sometimes you can get a lot of information by using more than one Riemann sum. Okay, so there are, technically, like it says, Riemann sums can be used at any point, but having a pattern, if the point can vary between any interval, it makes it really hard to form a pattern. So these are the 3 most commonly chosen ones. So let's look at a picture on the next page. Okay, so here is a region where we have chosen to do a left endpoint intersection, making rectangles with left endpoints only. So let's talk about this one. I'm going to approximate the area of the left Riemann sum. Back to notation over here, we often call these R sub L, R sub R, and R sub M for each of those, just to indicate which one's left, right, and mid as well. So we're going to approximate with the left Riemann sum. So R sub L is going to be, now first of all, I need to calculate my delta x. And so I know that A on this interval is 4 and B on this interval is 16. So this is the interval 4 to 16. And so when we calculate delta x, we're going to take 16 minus 4 divided by n, which they have told us we're going to use 6 right here. So that is 12 divided by 6, that is 2. Okay, so with that knowledge, I can fill in all of my xk stars since they're going to be the left endpoints. So the first one is going to be at 4, then I'm going 2 steps away to get to the next one. So 6, and that's where I would intersect here. My next xk star, the next left endpoint, will be 8, 10, 12, and 14. Notice that 16 is a right endpoint, it is not a left endpoint. Now, since we're doing the left Riemann sum, we want 6 subintervals, we should have 6 xk stars. All right, and so we are going to evaluate our function. We do have a function up here at each of those endpoints and multiply it by delta x, and that's going to give us our Riemann sum. So we're plugging in the left endpoint. So for the first one, our first xk star is 4, our x1 star is 4, so we have 3 times the square root of 4 times our delta x, which is 2. Okay, that's just f of x1 star times delta x. Now we're going to do it again, f of x2 star, so plug x2 star into the function, then times delta x. So plus 3 square root of 6 times delta x is still 2, plus the function is 3 square root of x, so 3 square root of 8 times 2, plus 3 square root of 10 times 2, plus 3 square root of 12 times 2, and plus 3 square root of 14 times 2. Okay, I stopped because I hit my last left endpoint. So that should be all 6 pieces that I need to add up. All right. Now it does say I'm going to approximate this area. I'm not going to get these in a simplified form. We're just going to approximate them by adding them all up. One thing I want to note is that in the future, I probably don't want to write times 2 by every one of these. We just want to factor that 2 out. So I'm going to do that when I type it in, and we'll get the approximation that way. So it saves us some time to think about these as, for this first one, I could think about any of these as having that delta x factored out. So it's delta x times the sum of f of x1 star plus etc. So that we have the delta x's all factored out. So, okay, so I need a calculator. I think I've got one here with not too much going in it. Okay, so I'm going to do 2 times, because my 2 is factored out, and then 3 times the square root of 4. Plus 3 times, you know what, they all have a 3, so why don't I factor that 3 out and not have to type that in either? Make it a little easier for me. So then square root of 6, I'm going to copy that, plus square root of 8, plus, I'm going to copy that with the plus, I think that's even better, and then square root of 10, maybe I don't want the plus in there, plus square root of 12 plus square root of 14. And that, because I factored the 3 and the 2 out, should give me, this gives me a estimate of 105.876. I don't have units on here, so whatever the units are, units squared, since it's an area measurement. Okay, now a couple of things I know about this one before I even get to the next one is that this area was all underneath the curve, and so I have a lot of error up here that I didn't get. So I know that this estimate is an underestimate. It's too small. When I do the next one, sorry, I was writing over there, underestimate, too small. When I do the next one, these are going to be too big. They have excess area in them that's not part of the area under the curve. So these ones are going to be an overestimate. It's not that lefts are always under and rights are always over. It depends on the shape of the curve. For an increasing function like this, you're going to have your lefts under and your rights over, but for a decreasing function, it's going to be the reverse. It just is because these are too big that they're overestimates, and those were underneath all, they were too small, they were underestimates. So now we're going to do the right Riemann sum. All right, so our right Riemann sum is, let's go ahead and keep that delta x factored out. I don't need to recalculate it because I already know it, so I'm just going to write delta x is 2. I do need to find my new endpoints. I don't use the left endpoint anymore, but I use my delta x to compute the rights. So I've got my 2 plus 4 is 6. 2 plus 4 is 6. 8, 10, 12, 14, and 16. So again, we are not using the 4 because at the left endpoint, we're using these 6 that are right endpoints. If n is 6, there should be 6 xk stars to plug in. All right, so we have delta x, which is 2 times, and then we're going to plug in each of our xk stars to the function. So that's 3 square root of 6 plus 3 square root of 8 plus 3 square root of 10 plus 3 square root of 12 plus 3 square root of 14 plus 3 square root of 16. Now, these are almost the same as the ones we had above. We do not have the 3 square root of 4. We do have the rest of them, then we have one more. That makes it easy to go back and just modify this line. I don't have the first one, and at the end I have one more, plus the square root of 16. And so this one comes out to be about 117.876 square units. Okay, now again, neither one is perfect. This one's too big, that one's too small, but by doing both of them, I know that the actual area is in between those. So I could average them if I wanted to and get a good guess of what the actual is. So if we do that real quick, the 105.876 plus 117.876, average that. So we can guess by averaging them that 111.876 is going to be closer, right? So that's going to be closer to the true area. Okay, so I just wrote a little bit on the bottom of the page, didn't show up, sorry. If I average those two things, we get a value that's closer to the true area maybe than both of those were. Now I can't always average them to get closer to the true area, especially if one of them is not purely over or purely under, but if they're both purely over, purely under, maybe I can get closer by averaging them. It's just something to think about. Won't always work because I don't always have all over, all under. Okay, like in this case. So now we're going to use the midpoint. We still know, because we're going from 4 to 16, that delta x is 2 on 6 subintervals. So since I want the midpoint, I'm only going to go halfway there. So I'm actually going to only add 1 to the first one. So that's going to be 5. So that's just plus 1, because I only need to get halfway there. Then I need to add the full delta x to get to the next center, and so on. So 5, 7, 9, 11, 13, 15, and then again 1 more to 16. And so we should have 6 new numbers. We're not using either of the 2 original endpoints right here. We're using those 6 midpoints. So this interval was 4 to 6, its midpoint is 5. That hopefully makes sense. Okay, so the function is still 3 square root of x. So the mid Riemann sum is going to be our delta x, which is 2. We'll factor that out. And then I need 2 times 3 square root of 5 plus 3 square root of 7 plus 3 square root of 9 plus 3 square root of 11 plus 3 square root of 13 plus 3 square root of 15. Okay, this one does not have any overlap with the previous ones because they both shared endpoints. They were going to not have so much retyping. I'm going to have to retype all of these, but that's okay. Okay, again, I can factor that 3 out, so leave it as 2 times 3, and then we're going to change the inside of the radicals to 5, 7, 9, 11, 13, and 15. Okay, and so this one gives us 112.062 square units. Okay, and that is another really good estimate. Now in this case, you have both under and over for all of these. So some of the error is canceling out. The error that is outside is canceling a little bit with the error that is inside. And so this is actually another really good estimate. Now, I don't know at the moment which of these is better, whether it is the midpoint estimate of 112.02 or if it is the average of left and right, which is the 111.8. They're close, but there's still a significant error. If we're talking like intense right here, we have a pretty good error. So again, we need to do a couple other things that could get us better. One of the things we could do is increase the number of intervals. If you did more than 6, you're going to shrink them and make the error on each of them smaller. So that could be something that could help. Okay, but right now, those are our area predictions. The area under the curve is going to be somewhere around 111.8 or 112.1.